Hello, good morning, everyone. Hello, how are you doing? Can you hear me?
Yes,
Yeah. Okay, are you alive and awake and active and patriotic? Shall we start? Okay, if someone joins later, that's okay because we have our recordings. So, first of all, do you remember what we have been doing last time? We're discussing the Byzantine fault tolerance protocol in its original formulation by Lester Lamport of early 1980s. All right. So today we'll first of all do a working example to see how this protocol works, really. Secondly, we'll consider as opposite to a very dated, not dated, but venerable, let's say, protocol from Lester Lamport, will consider a very, very, very modern incarnation of Byzantine fault tolerance, which is called hot stuff, BFT. And you will see that the main ideas from that Lester Lamport's protocol are still there, but it changed quite significantly, obviously, over the time. And the new protocol is not just for uh, any distributed systems, but it is specifically tailored to distributed ledger systems, to blockchains. And then this will also allow us to introduce an abstract notation first, an abstract meaning of smart contracts in the system, and then we'll proceed with discussing the actual systems implementing them. So, okay, let us recap, because these are quite important points. So a brief recap from last time. What is the purpose of the Byzantine fault tolerance protocol? Who can tell me? So why do we need it in the first place? What we are doing? What are we doing with it? You remember there was a distributed system with a number of legitimate nodes, let's say correct nodes, and a number of faulty nodes, which are called traitors, right? So what do they do? What is the characteristic feature? Let's recall. Otherwise, we wouldn't be able to move anywhere. So, what is the most important thing we can tell about the traitor or faulty node? Is it just a node which is down, not working?
it, uh, it says something which is not true.
It says something which is not true. Um, in that case, it is quite difficult to distinguish between a faulty node and uh, a legitimate node which for some reason has a different view of the universe, of the environment. You remember what happens? So generals surround the enemy camp, and then each one performs uh, reconnaissance and observes actually the state of the camp and draws a conclusion of what to do. For example, attack, wait, or retreat. Yes, the traitor, for example, may dissent from the others and propose retreat, whereas others propose an attack. Does it mean that he is indeed a traitor? Obviously, what he says is not the objective truth, but who knows in such a distributed system what is the objective truth? We're on a very slippery ground in this case, because if we define the traitor as being someone who holds views not supported by the majority, for example, 3 out of 4 say attack, and the traitor says retreat. So the one who dissents is automatically defined a traitor in this case. So you have a definition. Okay, you have a definition. The traitor of faulty node is a node which does not, let's say, broadcast the truth, right? Broadcast the truth to others. Okay, that's your definition. For example, traitor says retreat, others say attack. Which implies one who holds a minority view. Oh, that's a nice definition. Is a traitor. Which implies we're in 1937. That was precisely the definition at that time, actually, from history. The one who holds opposing or minority or dissenting views is a traitor. So clearly this doesn't work. That's not a definition, not the definition of a traitor. And a node of the system or Byzantine general, for the sake of the argument, can have a view dissenting from others, and they're still not a traitor. Now we have another statement. They broadcast faulty values. Okay, but what are faulty values? A faulty node broadcasts faulty values. Is the one which broadcasts faulty values. What are the faulty values? The answer is very simple. Faulty values are inconsistent values. So a faulty node, a traitor, is the one which sends inconsistent values. So it contradicts itself. So a really pathological liar, I would say. That's a much, much better definition actually of a traitor. If a node holds just a view different from others, dissenting from others, a minority view, he is not a traitor yet. Obviously, his view can be voted down by a very simple consistency algorithm, if you remember. Okay, nodes just collect information from each other. What do they propose? Perform voting, and a one which has a dissenting view can simply be voted down or can be overvoted by others. So that's okay. But a much more difficult thing is the node which contradicts itself by sending inconsistent values to different destinations. Because in this case, it can. So why do you think, this faulty node which sends different, random, inconsistent values is more dangerous than just a dissenting node? So what is really bad about this faulty node? Okay, this one just holds opposing views. Okay, we perform voting, we voted down. Attack, 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 retreat, we vote, and everyone agrees to attack. Very simple. What's wrong with this one in particular? By sending inconsistent values, it increases the overall probability. You remember? It increases the overall probability of confusing others. What does it mean, confusing others? Which means no consensus is reached in such situations. It doesn't say that it would always result in no consensus, but it would increase the probability of no consensus. Okay, we know that if there is no consensus, then what do we do? Legitimate nodes, if there is no consensus, perform some default action. Default action by correct nodes. And, well, correct nodes perform the default action. The traitor node, by the way, performs an arbitrary action, undefined arbitrary action by a traitor node. Okay? So that's the bad thing about the traitor. By sending inconsistent messages to others, it increases the chances of the situation when legitimate nodes would have no such an option, but to agree that they cannot agree and take a default action instead. Okay, what is good about the faulty node? Well, about such a definition of a faulty node. Okay, it sends inconsistent messages to others. That's bad from one point of view, as we have seen. But there is also such a certain thing which makes our life easy in this case. What can we do? Just, not from the protocol point of view, but from the common sense. What can we do if we know that There is a possibility, for example, for a single node which sends inconsistent values. What happened then? We can conquer potentially those inconsistent values by cross-checking them. So the problem can be, in many cases, fixed. We can attempt to fix the problem, but we can attempt to fix the problem by cross-checking all values. And this is precisely our BFT, Byzantine fault tolerance algorithm. Okay, now what? The algorithm we have defined and that is a very important thing to remember because the same property applies to a very large class of BFT algorithms. The most modern one, the hot stuff BFT, which we are going to consider later in this lecture, is based on the same property. So if n is the total number of nodes, let's say f or m, as we did in the previous lecture, is the maximum, not necessarily the actual, but maximum number of faulty nodes, operators, then what is the relationship actually between n and f? You remember, f should be small enough. We must have f less than n over 3, which equivalently means that n is greater than or equal to 3 times f plus 1. So for example, if f is just 1, so the maximum number of faulty nodes, maybe none, but at most 1, then we must have n being equal to 4 at least. Okay? Now, let us actually see, first of all, let us recall the properties, what BFT algorithm should do. So what we expect from the BFT algorithm? First of all, what would the BFT algorithm tell us about the behavior of faulty nodes? If a node is faulty, then what would the BFT algorithm do with the faulty node? Please, any ideas? Nothing. The BFT algorithm cannot change the behavior of faulty nodes at all. If they are faulty, they have an arbitrary, random, undefined behavior anyway. So there is absolutely nothing we can do with them. So behavior of faulty nodes cannot be fixed. It's undefined. Really, anything can happen. But correct nodes if they follow this BFT algorithm protocol, can ensure consistent behavior of themselves. That's the important thing. Okay, how? You see that I'm saying about consistent behavior, I'm inconsistent myself. I spelled behavior first in a British way with you and second in American way without you. So that's UK, that's US, as you probably know. Can ensure consistent behavior of themselves. And there are two criteria for that, if you remember. So first of all, um, if correct nodes let's say I1, I2 get a value from node J, but node J can be any, correct or faulty. And this get not a value, but get values. And those values are, well, some values. Then what do? They possibly modify those values, then they may get different values, but then they use a consistent value. So vi1 received from J equals to vi2 received from J. Remember, in our annotation, the first index is to destination, and the second index is from. Use means propagate or use in further voting. Or use in further voting. So basically, this requirement number one says, if correct nodes have received even different values from any node J, because that one might be faulty, then they somehow consolidate the values which they subsequently will be using. How do they do it? Obviously by cross negotiation. How exactly, we will see. Okay, and number two, Number two, furthermore, if in the example above, J is a correct node, so a correct node is sending values, then obviously vi1j equals to vi2j as received, so same values will be received, and same value will be used. By the way, please pay attention to the last point. Uh, the values which will be used are not necessarily the values which have been received. So in clause number one, in the requirement number one, we say, yes, we may receive even different values, but correct nodes would unify those values between themselves. Number two says, okay, but if they received correct values from originating from a correct node, then unification will not break them. Unification, or let's say cross negotiation, in one must not break correct values. Okay, so these are two fundamental properties of the algorithm, and you see that they are not really that much trivial. Now let us see a working example. We'll start with a very simple case with f equals to 1. There is only one faulty node, and the minimum number of total nodes in this case is 4. So we have 3 legitimate and 1 faulty node. Okay, please, let's just stop here for a second. Is everything clear, or at least appears to be more or less clear up to now? No objections? Okay, let's go. Now, what do we do? We consider our system consisting of, as I said, 4 nodes. Let's say node 1 is a traitor. How to spell traitor, by the way? With I or without? Faulty. Um, Nodes 2, 4 are correct ones. So initially, one very important point. When we introduced the algorithm in the last lecture, you have already seen that this cross negotiation, which was in that algorithm, is a recursive process. So if f is the maximum number of iterators, then we invoke this cross negotiation by reusing the same algorithm with the argument f minus 1. So effectively, if there is at most one territory, then the recursive depth is 1, and so on. So the recursive depth of this algorithm, recursive cross-negotiation algorithm, or cross-validation. Which question do we ask in this case? Each node not only receives values from other nodes, but it asks other nodes which values were forwarded to them by yet other nodes. And obviously you could do it endlessly. Ask node 1 asking node 2 to ask node 3 which value it has received from node 4. Something like that. But the depth of this recursion is limited, and it is equal to f. So we don't need to ask node 2 to ask node 3 which value it received from node 4. Only one level of cross negotiation asking each neighbor node which value it has received from another one, but only once, is sufficient in this case. So recursion has depth equals to f. In our case, f equals to 1 in the example we consider. So to begin with, let's draw those nodes. So that's node 1, and actually the values which node 1 sends to others are random. That's why we can't say any values here. I just put stars. They are completely random, so this is a faulty one. So, and this is step, let's say step 0 of the algorithm. So which values are internally held by node 1, the faulty one, we don't know, and it is absolutely immaterial. What we know is that it constantly lies by sending random values around. Not only sending random values for its own observations, but also sending invalid values when asked to transmit messages for others, as we'll now see. Now, okay, there is a node 2, node 3, generals 1, 2, 3, and general 4. Okay, what do? They initially have their own observations of what to do. So node 1 for itself, and that's why I use position number 2 here, node 2 in its own observation, position number 2, says attack. Node 3 also says attack. Node 4 is a legitimate one, not a traitor. And will I, by the way? Nevertheless, it says wait. It is little bit indecisive, but not a traitor. The traitor is here. Okay, the traitor is here. So what do? Step 0, each node sends a message to other nodes, use my value. So node 2 broadcasts its value to all other nodes. For node 1, it is absolutely unimportant which value it would receive. It is a faulty one anyway. But it says A to 4, and 4 writes A here as received from 2. It sends A to 3, and as I say, what it sends to 1 doesn't matter. 4 broadcasts its values to wait to 2 and 3, and 3 broadcasts again attack to 2 and 4. Again, to 1 as well, but it doesn't matter at all. Okay, so they got this. But that's only part of the story. Now, suppose that, yes, and node 1 broadcasts absolutely random values. So, for example, it randomly says retreat and wait. It sends retreat to 2, it sends retreat to 3, and for whatever reason, it says wait to 4. Okay? Now, you see that the value with the node obtained for itself in the second position for 2, in the third position for 3, in the fourth position for node 4, already firm values, AAW. Whereas values received from other nodes, I put in a smaller print, which indicate that they are not final yet. They need to be reconfirmed. They are not yet final. So let's see how this reconfirmation would work. So for example, the node number 2 has received a retreat from 1. It wouldn't accept this value immediately and use it in voting. By the way, you see, if the value is received as such, just, as written, then we can already perform voting on them. And if simple voting is applied, then what will happen? Node 2 says attack for itself if voting is performed now. Okay, dear students, please tell me, so what will happen looking at this? Suppose that we stop here, so vote and what happens?
So node 2 and 3 will attack, and node 4 will take default action.
And the default action in our case is what? You remember we agreed that the default action is retreat as the safest one. To retreat is always safe. To wait might not be safe because there is an enemy here. And it is quite dangerous actually to wait. In the presence of the enemy. So the default action is retreat. So if we don't do anything else, then two and three go for attack, whereas 4 retreats, and probably number 1 retreats as well because he is a traitor. So in this case, the enemy is attacked with only 2 divisions. So without further protocol action, only 2 divisions go for attack. By the way, if, for example, the traitor is consistent. Now, please, let's imagine the situation when the traitor is not really a traitor, but just a consistently mistaken general. So he consistently says retreat. What would happen in that case? So he sends retreat, retreat, retreat. What would happen? Then 2, 3, and 4, and by the way, 1 all, okay, 2 get, as we got, retreat, attack, attack, wait. So number 2 attacks, number 3 attacks, number 4 receiving retreat rather than wait would attack as well, right? And only number 1 retreats. So if number 1 is consistently sending retreat messages, so it is not a traitor, but just genuinely believing in retreat, then 3 divisions go for attack. If number 1 consistently says wait, but again consistently, then we have wait here, and number 2 is deadlocked in its decision and retreats. Number 3 gets wait and also retreats. Number 4 gets wait and also retreats. Now you see that an inconsistent liar, number 1, is really doing more damage than any consistently, genuinely mistaken general. Because if number 1 consistently proposes retreat, then nevertheless 3 of them would go on attack. And obviously attacking the enemy with 3 divisions is much better than attacking with 2. If number 1 consistently says wait, then 3 divisions would actually get deadlocked and retreat, which is probably safer as well. At least they would be safe. What happens with number 1 in that case if he waits alone in the presence of the enemy? Probably not so good, but nevertheless, it is a better thing than just launching an attack with 2 divisions. That's the motivation why we need this type of protocol. Okay, so what do we do then? Step number, I will use a color scheme. Step number 1. In step 1, the generals who received messages from others do not really blindly believe in those messages which they got from others. So, for example, number 2 got retreat from 1. He wouldn't just think, okay, I got retreat from 1. Let me ask others what they got from 1. Again, from 1. So instead of just one message got from 1 here, there would be 4 messages got from 1. Here as well, instead of 1 message got from 1, there are possibly 4 messages from 1. Okay, so which number two received really retrieve directly from 1. So here is really retrieve. Number 3 received retreat directly from 1. Yes. Number 4 received wait directly from 1. Directly. But now they exchange all those exchange information about what they got from number 1 between each other. So they forward to each other messages they received from 1. So step 1, consolidate which message they got from 1. Okay. 2 says to 4 that he got which message from 1? Retreat. Therefore, we put a retreat here because 2 told 4 that he got a retreat, whereas 4 tells 2 that he got wait from 1. 2 tells 3 that he got retreat from 1. 3 tells 2 that he also got a retreat from 1. And 4 tells 3 that he got wait from 1. 3 tells 4 that they got 3 tells 4 that they got a retreat from 1. You see that in those 4 cells, obviously one cell is unfilled because this is the current node itself. So it doesn't have anything to tell itself. He got a retreat from 1 directly, and also number 3 told 2 that he got a retreat from 1. Number 4 told 2 that he got wait from 1. And now these values can be consolidated by taking a majority. Obviously, the empty one becomes empty. So here we are dealing with n minus 1 values. N minus 1, which is 3. We are consolidating n minus 1 values. So the consolidated one here is, that's what we got directly, that's what we got from others. So that's direct. That's from others. Now consolidated. The consolidated is retreat. Consolidated is retreat. Consolidated is retreat. So we got, in spite of number 1 sending random messages, we got a retreat. Should, for example, number 1 send all different messages, attack, retreat, or wait, we would have 3 different ones here, and then we would still get a retreat. Because in that case, no consensus could be reached. Okay? Now a more interesting thing. Here, the source of the message was a traitor, and 2 legitimate lieutenants, or, well, okay, other generals, were consolidating the messages they got from 1. Now, step number 2. Step 2. consolidate which method they got from 2. And here the things become interesting. Consolidate which message they got from 2. So in this case, 2 doesn't need to consolidate anything. We are considering 1, 3, and 4. Well, 1 is out of question again. He may not consolidate anything. He is just outright faulty. So in this case, it is interesting to see how 3 and 4 consolidate which message they got from 2. Originally, they both got A from 2. Okay? Originally, this is A. And that's why I put it in blue. So originally from 2, they got this A and this A. But now, number 3 is asking 1 which message they got from 2. Number 3 would ask 1. Number 3 would ask 4, would ask 2, and so on. So 3 of them are participating in this consolidation now. So, okay, what do you think happens? Number 3 is asking 1 which message number 1 got from 2. What would number 1 say? What do you think? Number 1 would again produce a random answer. Number 1 is a randomly behaving faulty node. So suppose that it randomly sends a retreat or wait. So here, for example, we would get a retreat. In fact, of course, number 2 sent A to 1, but it doesn't matter. 1 says, no, I got retreat from 2, as reported by 1. Now, what would number 1 say? Okay, then again, a random value would occur here. So for example, wait. And here it doesn't matter because it knows its own value anyway. So again, we got inconsistent values reported from 1. We were asking 1, which value have you got from 2? And we got inconsistent values. Now, of course, when we ask for number 3, we don't ask anything. When we ask 4, which value you got from 2, it correctly says A. And when number 4 asks number 3, which value you got from 2, it also says A. Now we perform consolidation. Attack. And here wait attack, which is also attack. Okay. Now the final thing remains, well, almost. We need to, for example, to finish with number 4, we need to consolidate the values it got from number 3. To finish with number 3, to finish the values it got from number 4, and so on. So continuing this way, well, let's probably run this to completion, so you will see how we eventually rectified the problem. Okay, now step number 3. Step 3, consolidate which messages they got from 3. Okay, from 3, originally they got from 3 originally obviously they got A here, here it is 3 itself, and A here as well. But now when we do consolidation, when we ask other nodes which messages we got from 3, what happens? So what do I put in the first position here? A random one. So suppose there is a weight here. What I put in the second position, of course, nothing. What I put in the fourth position? The fourth one correctly says that from 3 I got A. Here, in the first position, a random one. So for example, retreat. In the third one, it correctly got in the second one, it got A from 3, so it is A. So again, we have a consolidated value, which is A here, which is R and RAA, A here. Wonderful. Now the final round of consolidation. Which color should I use? Black. Step 4. Consolidate messages. Consolidate messages they got from 4. So what have they got from 4? We first propagate the values which they got from 4 directly. Okay, I will not change color, you understand. So number 2 got from 4 directly weight. Number 3 got from 4 directly weight. Now, they ask number 1 what they got from 4. And number 1 again says inconsistently. It says weight here, retreat here. 3 asks 2 what they got from 4 and obviously receives weight. 2 asks 3 what they got from 4 and obviously receives weight. So now again we can do a consolidation. Here is unconditional weight. Here it is weight as well. So finally, at the completion of step 4, we have the following values obtained by each node. Number 2, RAAW. Number 3, RAAW. Number 4, number 3 is again RAAW. And that is a very important thing. So we have really satisfied the property that now all legitimate nodes will use for final voting, all legitimate nodes will use the same value, the same set of values. Obviously, in this case, all legitimate nodes vote for attack. All of them eventually vote for A. And we achieved our consistency objective. So the protocol now tells us that we attack the enemy with 3 divisions rather than 4. Well, obviously rather than 4, but rather than 2, as it could have happened without using this protocol. Okay. Any questions about this? Please note that the recursion depth which occurred here is indicated by precisely this horizontal bar. We first received just one letter, and then we cross-negotiated with our neighbors which value they received from the same source, so we would know. So recursion is here, okay? The recursion in our algorithm is here. If you like, but it is going to be tedious, you can consider f equals to 2 and 7 nodes. It's not that the number of nodes is bigger, but what would happen, what would change in this picture if we select the total number of faulty nodes equal to 2? Can you tell me, please? For the moment, there was only one faulty. If we select 2 faulty nodes, what happens?
The total number of nodes increases.
The total number of what? Of nodes?
The total number of nodes has to be increased.
There will be 7 nodes. That's true, because we have 3 times f plus 1, so there will be 7 nodes if f is equal to 2. That's absolutely right. But that's not the biggest problem. What is the biggest problem in that case?
The recursion depth will be equal to 2.
Yes, indeed, you are absolutely right. The recursion depth will be equal to 2. So we would not simply put this value as received by another node, but would first ask them to negotiate what to reply to us. And then becomes difficult. I wouldn't even endeavor to do this recursion depth equal to 2 here. In almost all practical cases in the past, in distributed systems which are not blockchain systems, but simply used for, let's say, inversion programming, as we discussed in the first lecture, for, let's say, correcting faults in safety critical distributed real-time systems, then it was really f taken to 1 and n taken to 4. We wouldn't even proceed to 7 in that case. And by the way, it's interesting that for this algorithm, the total number of nodes should be, for example, for f equal to 1, it shouldn't be odd, it is even. And the presence of 4 nodes allows us to reach this interactive consistency property. That's how the classical Byzantine fault tolerance works. Okay, let's make a short break and we'll... Yes?
Next question.
Yeah.
Does it mean that if, for example, we have n faulty nodes, when we need n no f faulty nodes, when we need n in the power of f messages to communicate?
You are right with this question, actually. So yes, how many messages? Let's compute. Actually, how many messages do we need? It would not be really that many, because you see that each recursive step down, it would require communication between lesser number of nodes. So, for example, here at recursive step number 1, we require communication between n-1 nodes. And n-1 nodes send messages to each other, generally with respect to n-1 messages received from us. At the recursive step 2, you would involve only n-2 nodes negotiating the corresponding values between each other. So if, for example, we need to negotiate this value, if you can see my mouse pointer, then it would require only 2 nodes in the second recursive step. So the number of communications in that case remains limited, but it would still be of the order of, fortunately, not the number of recursive, not the power function, but I think it is going to be something like n cube. So it would not explode, but it is still quite tedious to draw. You can do it as an exercise, actually, to consider this algorithm in general and the number of communications involved. I think it would be of this kind of order. Okay, so let's make a short break and we'll continue with the modern incarnation of this protocol, which is hot stuff BFT, again, Byzantine fault tolerance. Okay. Welcome back. Some further questions about this. What do you think? If we consider this Byzantine fault tolerance as just an algorithm with inputs and outputs, what do you think is the input to the whole algorithm we have considered? Well, it does something, so it performs some actions. But each algorithm typically has an input, then a magic step when really magic occurs, and an output. So what is the input to this Byzantine fault tolerance, as we have considered it?
It could be the values received from other nodes.
No. The values received from other nodes to be received from other nodes should first be obtained by other nodes. I would say that the input to this algorithm is precisely the values initially observed by the node themselves. Number two observes the camp and decides to attack. That's the input. This is the original observation, which didn't come from any other message. All other values are just propagated, consolidated, processed somehow. The original ones are those which are big characters. This one, and this one. So these are the inputs of the correct nodes. So the total input is precisely their initial observations. Maybe number one also made some input here, but this input is not at all used. It is irrelevant, because irrespective to the input made, number one is sending random messages. Retreat, await, randomly. But the original inputs are here. Okay? And what is the output? If there is an output.
Consolidated value.
A consolidated value. So these three inputs, star AAW as inputs, result in a consolidated attack output. Indeed. Now, if we consider this model, and we should really do so, because what we are studying is distributed ledger systems, so not general tactics in military, right? Therefore, if we consider this model, then we would like to probably make use of it for our distributed ledgers somehow. So let us think. If we map this algorithm or this protocol with the inputs as depicted and an output to a more familiar setup of distributed ledger systems, what would it mean? For a distributed ledger system, what is the input? Let's go back to our Bitcoin. So what is the input to Bitcoin? Suppose that the Bitcoin network and the Bitcoin protocol is just one big distributed algorithm. What is the input to that algorithm? What do you think? Well, if it does something, it processes some data, then there should be some input.
I believe this is the entire chain.
The entire blockchain is the input. Not quite. The entire blockchain is the state of the algorithm, the internal state. The input is something which is new. It's new data which are flowing into the system, and changing as a result the state and possibly also resulting in some output, or maybe not resulting in the output. So the entire blockchain is the state of the system and not the input. What is the input?
Maybe a new block.
Almost correct, but a new block is again not a raw input. The new block is formed by miners and then hashed. So, okay, what is the new block made of?
Transactions.
Transactions. So the input to the system are transactions. New transactions are coming in, and as a result, new blocks are formed. The first successful block is hashed, and the system state is updated. By the way, there is no visible output to the user. Apart from the fact that there are messages on new blocks, actually we can say that the whole blockchain is the state, transactions are inputs, and each subsequently hashed block is also an output, because it is sent around, and by running an observing node, not necessarily a hashing node, it can be observed, something like that. So a new block both becomes part of the new state and acts as output. Transactions are inputs. So what is important about that is that we have a continuous stream of inputs. There are new and new and new and new transactions being added to the system, right? Whereas in the distributed Byzantine fault tolerance we have considered here, there is only one input. The generals make an observation once, looking at the enemy camp, and make this, who knows what, AAW distributed input into the system. This is distributed input. Each node has its own portion of input, all right? Nevertheless, it is an input. So in the system we have considered so far, there is only one input and one output. Whereas in a blockchain system, there are periodically, well, not periodically, but let's say aperiodically, at any time, new inputs. And generally, roughly periodically, roughly every time in 10 minutes, we have outputs and state updates. Something like that. Which suggests that as a very, very simple model, the Byzantine fault tolerance we have considered corresponds to what? So if we compare what we have drawn here in our whiteboard, compare it with the blockchain of Bitcoin. Here there is a single input and a single output. In that case, there is again a distributed, some kind of distributed consensus algorithm, which we have already started with leader election based on proof of work, who was the first able to prove the work committed, and aperiodic inputs and quasi-periodic, let's say quasi-periodic outputs. So if we compare the two, I'm just, why I'm asking this is because if we don't clarify that, then this Byzantine fault tolerance we have considered and the hot stuff BFT, which we are now about to consider, would look quite dissimilar and maybe not even having much in common with each other. But in fact, they do have a lot in common. So looking at this, what would it correspond in a blockchain system? What do you think? Map this onto a blockchain of Bitcoin network. What would it be? our inputs AAW, what would it be in the blockchain setup? Consider the Bitcoin. Well, here inputs are observations. In that case, inputs are precisely the transactions, right? Here we may have inconsistent inputs. Each general has his own observations of whether the enemy camp is vulnerable or not. In that case, we have different transactions flowing into the system. So in the Bitcoin blockchain world, inputs would correspond to transactions, as we already know. And indeed, you see, so there is a close analogy here. Inputs are first not consolidated in a similar way as transactions are coming into individual blocks first. But then there is a protocol according to which these transactions are, first of all, consolidated across all of them, well, distributed across all of them, and then consolidated. Yes. Okay, so these are transactions. Output, which we consolidated here, is a kind of new block. And a new block corresponds to just one round, effectively, one round of, let's say, Bitcoin, BTC blockchain operation. From which we make a conclusion that the Byzantine fault tolerance we have considered here could be a simple model of just one round of a more general protocol used in some distributed ledger system, right? Here we have just, one round of inputs, consolidation, output. And a similar thing we have in any typical blockchain. We have a round consisting of, well, a periodic, of course, inputs, but then at the end of the round, something like a new block emerges. So this is just a very simple model we have considered so far, a very simple model of a one round of a typical blockchain. Okay, so now let's see how a real blockchain would work. A real blockchain would use a somewhat similar protocol, but to begin with, it has the concept of rounds embedded into it. So it will be multi-round by definition. Here it was for one round only. Okay. Now it is clear where we are. We consider this hot stuff BFT, actually hot stuff without a space, which is a protocol not invented by, but widely used in the Libra network. You remember what Libra is? Or was, actually. What was Libra? It was an ill-fated cryptocurrency from Facebook. Facebook, based on its huge community, nearly 2 billion probably now, of users, was trying to launch its own cryptocurrency, which would be accepted within the community. But the United States regulators prohibited eventually the company to do this. And because it was not allowed in the United States, they decided not to do it at all over the world, because first of all, obviously, without the US customers, it would be hugely incomplete from the business point of view. And secondly, they could face even further sanctions from the US Department of Finance, the US Treasury, maybe some other regulatory bodies, if they did it even outside of the United States. So as a cryptocurrency, Libra is kaput. But as a technology, Libra network is very much, well, Libra network is defunct, obviously, but hot stuff DFT as a protocol plus some other components from the network are very much in use. And the protocol appeared to be very, very useful. It was not invented by Facebook, but they provided a good implementation and tuned this protocol for the requirements of Libra. So let us consider how this protocol works. So first of all, there is a fundamental concept of round. It is a kind of clock which is ticking in the node. So there is a round number. In the hot stuff BFT, it is also called view. So a round number is actually a view number. They call it view, but it is probably more correct to call it round. What else? It is a leader electing protocol, but unlike the blockchain of Bitcoin, election of the leader in this case is very simple, at least in the version which I'm going to discuss, because we, in this case, assume that it is an authorized network. And in this case, we can simply elect the leader, not based on whatever proof of electricity stake, whatever he submits, but simply on a round by round basis. So each round would be a new leader. We have a certain function, deterministic function leader of the round number. Obviously, if a certain node becomes a leader, but then doesn't fulfill its functions, then the leader is dismissed simply by a timeout. So suppose that there are nodes. So at each moment, there is a current leader, and other nodes which are called replicas. But don't mistake it for a centralized system. In the next round, once this round is completed, a completely different node would become a new leader, simply because we have this leader election function. So it is not centralized. Each leader is very temporary for one round only. Okay, the inputs, and by the way, we say there is a round number. Where is the round number? There is no such a thing as a distributed notion of the round number. Basically, each part of each node has its own round number in its state. Here, it may be different from the current round number in another node. Nevertheless, there is a certain consistency which is achieved about the whole state of the system, including the round number. What else? There are incoming transactions. So transactions are coming into different nodes, and yes, of course, they are propagated to other nodes similar to the Bitcoin blockchain. But I would say that again, there is absolutely no way to synchronize the transactions, pending transactions in each particular node. And that's why we can say that each node has its own list of transactions, of pending transactions. Furthermore, this list of pending transactions is not even a list by itself. Well, the protocol uses the term not transactions but commands. What is interesting is that it is not even a list. Why it is not a list? It is not a list because if you remember, even in the blockchain of Bitcoin, the internal state can fork. So, for example, we would have a sequence of blocks originally available. Then two hashing nodes would almost simultaneously produce a new block and exchange the information with each other with new blocks containing new transactions being appended to different blocks. As you remember, a fork could occur very easily in that case. So in this protocol, we're not talking about blocks. Blocks, after all, technical detail that we put transactions into blocks. Why do we do that? Simply for efficiency, so that instead of just hashing each individual transaction, which we could actually, we had the entire block. As you remember, it is only an implementation detail. It doesn't matter. So here, transactions are all identified. So let's say there is a transaction ID. And they put at each node, the pending transactions are put into a list. So there is a transaction ID. And the actual transaction is probably a pair, transaction ID, and maybe a list of, I would say, the list of actual commands within this transaction. Commands are some abstract operations which, after all, will change the internal state of a particular node, and by this consensus algorithm, will change the internal state of the whole hot stuff BFT network. And because we organize these transactions in a tree, then this is a typical node, so a transaction ID comments, and we also have the parent transaction ID conceptually. So then it is a tree. Okay. So for the moment, let's say that each block corresponds to just one transaction. It has one ID, transaction ID, but it may have just any number of commands which affect the state. By commands, there could be just simply data blocks, which are data chunks which are appended, or maybe smart contracts which are executed on the data, maybe something else, maybe instructions to insert smart contracts themselves into the network. So we do not detail what the commands are here. Okay. Now a very important point. Let us go back, and we have already mentioned that looking at this diagram. So nowadays, you see, we assume that communications in the original BFT are such that we do not lose messages, or at least if we lose a message, then we have a timeout and we replace it by an empty default value, which in that case is retreat as well, which means that all in all, messages are not lost. And we can always, the messages are not altered in transit. So if a message is sent, then it is delivered as it was sent, and we always know the sender of the message in this case, right? So a random message can come from the traitor, because he really sends random messages, not because messages can get corrupted in transit, and not because number one can intercept others' messages and forge them. Only when we ask number one what, for example, number two sent to you, then obviously number one is of no obligation to propagate the original number two message and can report an arbitrary value. But let us think. With the modern cryptography, because that protocol goes back to early 1980s, when, yes, digital signatures were just introduced, the RSA standard was not just a standard at that point. The RSA patent was obtained in 1977. So what could we do better in using modern cryptography for this setup? We could disallow number one to lie upon the messages he received from others. So when number three, for example, asks here number one which message it received from number two, number one can report an absolutely any value. Okay, for example, here it reports retreat, whereas in fact it got attack. But if we have a chain of digital signatures, so first of all, there is a message signed by number two forwarded to number one, and then number one does not generate a new message to say number two told me this, but simply forward the original number two message signed by number two, adding his own signature, then this wouldn't become possible. Then by imposing stricter cryptographic requirements, we would probably not even need this second order this complicated second order consolidation. So we would, the whole process would be simplified, because in that case, we would be sure that all other nodes report similar values to us as received by other nodes, as we would receive from those nodes directly. So we need to think what kind of cryptographic, first of all, cryptographic safety requirements or safety conditions are imposed on the modern hot stuff, unlike this 1980s setup of the original BFT. So what we say in the following. So there are indeed, again, F, at most F faulty nodes. And the total number of nodes n is greater than or equal to 3f plus 1 as before. So this condition still holds. So what are the faulty nodes? The faulty nodes are compromised ones, obviously. So they may have very legitimate public and private keys, but they can do whatever they want, and we can say they are under control of the adversary. What about legitimate nodes? The whole algorithm works, and this is a very important feature, when it performs voting. Then the voting is performed based on k out of n votes. So this can be implemented by digital signatures. We did not consider that example in very detail, but there are multi-party digital signatures. Again, you could implement them, for example, based on a more advanced form of elliptic curve cryptography, in which case a signature is validated, the whole signature, provided that out of maximum n nodes, k of them have signed it. Okay? But the question is, unfortunately, we don't know who this k could be. And it is entirely possible that if, for example, this k is taken to be sufficiently low, for example, k is less than or equal to f, then it would be all faulty nodes which signed an agreement used in this voting. And that way, faulty nodes would be able to overcome and take over all operations of the whole network. That's probably we don't want to, all right? So what we want, what do you think would be a reasonable requirement? So what kind of value for k should we reasonably expect? Well, it is probably reasonable, mostly based on cryptographic considerations, that okay, you have k minus f, which is the minimum number of completely valid signatories. When you sign something, okay, there are at most f faulty nodes, but k minus f are valid ones. minimum number of valid signatories. So what do we want about k minus f? That it is to be greater than 0. Obviously, yes, but it is probably not sufficient. We want a stronger requirement that k minus f is greater than f. Why this requirement? By itself, it is not in the not directly used in the protocol, but if the number of valid signatories is greater than f, then the probability, as comes from just the underlying cryptography implementation, the probability that faulty nodes could forge a legitimate signature becomes infinitesimally small. So this is simply for a requirement for cryptographic stability. Because we did not consider the mechanisms of multi-party digital signatures. We only considered a very simple single-party digital signature algorithm based on elliptic curves. We cannot prove actually the importance of this requirement, but get it for trusted that in this protocol this kind of requirement is used. So it's that's for cryptographic stability. Okay. Now, which obviously means that k is greater than or equal to 2 times f plus 1, whereas n is greater than or equal to 3 times f plus 1. Okay, now consider what would these nodes do. This is a multi-stage protocol, and there are stages which are commonly known as, actually there are 5 of them, and we're going to go through them in sufficient detail. So as well as in the original Byzantine fault, we had, how many stages could we identify in the original Byzantine fault tolerance? You see, there was a stage 1 generation of inputs, stage 2 propagation of these original inputs to all other nodes, then a recursive step negotiation of common values by asking other nodes what your neighbors told you. That's number 3. Number 4, final voting, and number 5, probably action on the voted value. So also not a single step. Here in the hot stuff, we have phases which are called prepare, phase pre-commit, commit. These differences between pre-commit and commit, as well as prepare, they are dictated precisely by distributed locking and commit properties, which are essential in order to ensure correctness and liveness of this algorithm. And finally, there is a stage which is called decide. Let's try to go through them. Okay, what would happen in the prepare stage? Prepare stage is the beginning of a new round. So now we're at the beginning of round n. Okay, beginning of round n. Let's say n. There is a leader for this round. So there is a current leader for this round n. It will be different one for the next round, which is determined, obtained deterministically from the round number, as we know. So what would the leader do? So in each stage, we have an action by the leader, and we have an action by the replicas. They're not really replicas, they're just all other nodes apart from leader. So there is one leader and n minus one replicas. Okay. What would they do? What do you think the leader should do? A newly elected leader should do at the beginning of the round? What do you think? The previous round concluded with some kind of common state, right? So there is some kind of common agreed state which was committed and decided, we'll see what it means, at the end of the previous round. Now a completely new leader was elected just by taking a random, maybe a random number, maybe just a sequential number modulo the total number of nodes. Somehow a new leader was elected. It is not at all clear whether the new leader is indeed one of the committers of the state from the previous round. It may very well be that the new leader was left behind, actually. So the first thing it needs to do at the beginning of the round is to consolidate its own view of the previously committed state. So it needs to get up to the previous state. Okay? There are several message types which are exchanged between the nodes in the system. I will introduce them gradually as we go through the algorithm. So the first thing the leader should do is to wait for, well, ideally it needs to wait for all messages confirming that other nodes, non-faulty nodes actually, have completed the previous round and distributed their own state. Including this means that because the messages were broadcast, it would wait for its own message from the previous round confirming that it finally enters the new state, which might not be immediate. So this, in the original protocol formulation, these messages were called new view, but I would call them new round. It is more clear. So it would wait for all messages from all nodes apart from possibly faulty nodes. We know that there are at most f faulty nodes, so n minus f messages of type, let's call the message type is new round, indicating that a new round is starting, and containing the round number of the previous one. So which really means that the previous round has now been completed. If we are now at the beginning of round n, then it would wait for messages new round with the previous round n minus 1. Now suppose that those messages have been received. What would this message actually contain? the messages would contain from all nodes have completed the previous round, but we need to select the latest state among those messages. So in that case, the leader, because it is now a leader, it would extend the latest state, which is extracted from the previous round, by new transactions. So new input really comes here. They are coming to the leader at this stage. And inside the leader, because each one, as you remember, it contains its own transaction tree, it would append its own transaction tree with basically a new leaf. So it would take the latest node from the previous transaction. I would say it is so-called current proposal. This transaction is not final at all. It is a proposed one, but final current proposal is, let's say, highest node to which we append highest transaction node in the tree, to which we append new transactions. Sorry, append new transactions. So taking the latest final state, and because it is a leader, it creates a new candidate for the new transactions. Okay. What it does then, this proposal, what do you think? So the leader has created the proposal. What should it do then? Well, it is a distributed consensus system. So if the leader has created a proposal based on the highest previous state and new transactions, then probably it needs to broadcast this proposal to all other replicas. Very much like for the Bitcoin blockchain, a new incoming transaction is first broadcast to all other nodes. So it would broadcast a message and now this message, in order to distinguish it from the original one received here, would have another type. So this would be typically at the end of each phase, a message is sent with the type same as the name of the stage. So it would say, it would broadcast the message called prepare, containing, effectively containing this current proposal. What would replicas do? So that's the leader. Replicas would, at this stage, would not proceed further until they receive this message from the leader. So replicas wait for this prepare message each replica is waiting for message prepare with the current round number n and containing this current proposal. Okay, a replica has received the current proposal. For message from leader, of course. A replica has received the current proposal from the leader. What would it do? A replica may have its own forked state, which is inconsistent with this current proposal. So it has its own tree, and maybe the leader has extended another branch of that tree, not the one which, well, maybe it doesn't have that branch at all, or maybe it has several branches. So what the replica needs to do is actually it would accept this proposal from the leader only if the current proposal extends the current branch of the replica. So if the current proposal extends, it's not at all the case, extends one of the branches at least, and that's why I say a branch in a replica, the replica says in that case to the leader. There are some other checks performed at this point, but they are more technical, so I do not dwell on them. In that case, the replica confirms to the leader that it has accepted this proposal. Confirmation is done by this time not broadcast, but just a send message, because it goes only to the leader, which says it is again of type prepare. We don't need a separate type here because the leader actually knows where the message comes from. In the first case, prepare is sent from the leader to replicas. In the second case, prepare is sent from replica to leader. So same message type is okay in this case. And this prepare contains what? So first leader proposed a state extended by itself to the replicas. Now, if a replica finds its own state which further extends the proposal, then what do you think would this reply contain? What do you think it would contain? It would contain that extended state from the replica. Extended state from replica. Okay. We are now in the pre-commit stage. What does the leader do in pre-commit? The leader obviously waits for those extended states from the replicas. Again, wait for not all of them because they could be faulty, n minus f prepare messages from replicas. Okay. Got them or got a timeout and an empty state somehow. What would it do? Once it received them, you see that each of them extends the original leader state. But these extensions may be inconsistent. So what it would do, it would generate current proposal prime, which is basically the vote on cryptographically signed with combining signatures at least k, if we vote at least k prepare messages from replicas. Those. And here the message is sent, here the message is received. Okay. Once this vote is performed, then basically the leader has got yet another proposal, now consolidated across the replicas, which it would obviously broadcast. As a new type of message, which is now called pre-commit, as the end of the stage. With this current proposal prime. Okay. Now basically, okay, what would replicas do in this case? So it's a little bit early to come to the commit stage. We still need to see what replicas do in pre-commit. Replicas, if the leader broadcasts messages to them, then basically they wait for those messages. Wait for pre-commit from leader. Which contain this current proposal prime. And in that case, because the leader has already done consolidation of voting, then the replicas must accept it. So the replicas by themselves, upon receiving this message, would set their own, let's say, would set their own prepare state to this current proposal from the leader. Now, okay, and it would, after that, after receiving, it would need to do what? The leader still doesn't know that the messages have been received, so they need to send some kind of confirm to the leader. So send message, which we would say pre-commit, to leader. We now come to the commit stage. Okay, so now this unified view has been distributed by the leader and accepted by all valid replicas because the leader has done the job of consolidating the state for them. So the commit stage is a technical one. It is really to ensure if and when we put the we prove the correctness of this algorithm, then it is the commit stage which is required. So basically, it is one more cycle of waiting on yet another locked variable. So I would say, without giving you details, locking messages exchange. This is basically to guarantee the distributed locking of the whole stage, which is a technical requirement. No data are essentially updated here, so this is technical, ensures safety and liveness. And it is a similar thing actually. So the leader is obviously waiting for the pre-commit messages from the replicas. Then some looking, then broadcast commit. Looking, broadcast commit. Sorry for my handwriting. Eventually, replicas on receiving that would confirm commit to the leader. As I say, no more meaningful state updates occur here. This is only needed for yet another distributed synchronization, which is used in order to verify the correctness of the whole algorithm. And finally, that's all. So then there is a decide stage. And at the end of the decide stage, so far, the new commands have been only included in the proposal, but they were not yet executed. So now we consolidated finally the stage. It is a similar exchange, and now execute transactions in all nodes. Output to the client, if any. And eventually, in order to complete the thing, what do you think we would do? Elect new leader. Deterministically with a round number of n+1. And you remember the first at the first stage of the whole process, the new leader waits for the confirmation new round messages from all clients, which mean that all clients, sorry, all replicas, meaning that they're all done with the previous round. So all replicas, including alt leader, send new round message. To the new leader. And we're going over. So this is an outline of the algorithm, including basically multi-stage synchronization. And what is important is that we don't really need to, in order to commit the state, we don't really need to wait for all nodes. We don't even need to wait for all correctly operating nodes. We only need to perform, in voting, we need to perform consolidation of k nodes, where k is 2 times f plus 1, where the total number of nodes is 3 times f plus 1, which makes this protocol to be very lightweight and suitable for high performance implementations. And also you see that there are multi phases, but there is no recursion here. The total number of messages distributed is what is the asymptotics, the order of magnitude for the number of messages being sent in the whole protocol in one round. It was cubic with respect to n in the original one. What is it here? Per each round, how many messages do we send? Roughly. N? You said n?
Yeah.
You are right. You are absolutely right. Not even n squared. We send of n messages. So it is a huge, huge, huge advantage compared to a cubic, or maybe even of n times n cubed number of messages in the original Byzantine. So the total number of messages O of n. Informally, we do not formally verify this protocol. I just gave you an outline. Informally, why is it happening? What are the two factors which allow us to do this? Compared to the original BFT, we got a huge reduction in the number of messages. By which
We
means?
don't need to broadcast messages by each node, but rather one leader will send all the messages by itself.
You are absolutely right. So first of all, advantages. You're absolutely right. So first of all, we have a leader at each round. Okay. Second, what else? This might not be directly obvious from the algorithm, but we know that the messages are cryptographically signed. So, and signed using a very advanced form of k out of n signatures. And k is sufficiently large. So when the leader gets information from all the replicas and perform this vote here, then the leader doesn't need to worry about, let's say, unauthentic or any other type of messages. it really knows that, well, it may very well be that apart from those k, it receives misbehaving messages from misbehaving nodes, including faulty ones, yes, maybe. It waits for n minus f messages, yes. But it doesn't really mean that it receives only messages from non-faulty nodes, not of course. It can receive messages from any nodes. Nevertheless, this digital signature protocol with k out of n, with k sufficiently large so that not just k is greater than f, but k minus f is greater than f, if you remember here in this stage. It allowed the leader to correctly unify the messages without this cross-examination. So basically that's all about the protocol. Liber is dead, but our own project at Innopolis University, which is called InnoChain, is based on this hot stuff BFT with some modifications protocol. It was our plan actually to talk a little bit about InnoChain, and I will give you some outline. So yes, it is based on this protocol. It is a formally verified distributed ledger solution, which first of all has smart contracts with formal semantics. Where are smart contracts in the example we have considered? They are so-called commands. So when the commands are applied, in particular, it means that the commands are some kind of executable code which act upon themselves or execute transactions. Transactions may contain executable scripts. These scripts are run either in a virtual machine or using some other technology in the chain. Smart contracts are written currently. Tell me, please, you have probably had already some kind of course on functional programming. Most of you. Haskell. Or not? Have you seen the functional programming paradigm? Functions are first-class values in your programming language. You can create new functions on the fly. The most important citizen in your language is a lambda expression, which indeed creates a function on the fly. Functions can be return values of other functions, can be arguments of other functions. They can be stored in data types, anything like that. Functional programming. No?
We had an elective course in Haskell, but I believe it's a small part.
Well, Haskell is very good as a modern and probably the main modern functional language. So yes, we are basing our technology on a somewhat older functional language, which is called ML. ML is just meta language, not machine learning. ML is a functional language originally developed in 1978. It has a so-called strict evaluation compared to lazy evaluation in Haskell. And it still has some rudiments of imperative programming. So for example, if you really want to, you can create updatable variables. In a pure functional program, you can't do that. but it has a very big advantage, which was with ML language from the very beginning. ML was created for its use in automated theorem proving and automatic verification, formal verification of software correctness. So ML is coming in conjunction with computer logic system, in particular high order logic system, which allow you to examine ML programs or programs written in a language like ML and prove certain properties. For example, in some cases when you can, not always obviously, but when you can, you may attempt to use this system to prove program termination. How? If, for example, it uses a fault type structural recursion over a finite data type, then you know, of course, that there would be a termination. If you, on the contrary, use completely arbitrary undecidable recursion, then you might not be able to prove that. It is undecidable even if your program terminates. So we in particular, we use a version of ML language in the implementation of InnoChain, which is called CakeML. And CakeML is closely linked to a high order logic system, which is called Whole4. Which means that for smart contracts, we'll then study smart contracts in Ethereum, but I give you immediately an overview of InnoChain, so we would not then spend time returning to this system, unless you are interested and you come to work for this project, which is quite possible, and you are welcome to contribute. And some of you actually do it already. So the language for smart contracts could be either the language, the internal language of Whole4 or CakeML, or any language translatable into CakeML or Whole4 in terms of generating abstract syntax state. So for the moment, for example, we have a smart contract which is being developed in Whole4, which is then automatically translated into CakeML. And what is important is that CakeML has a formal semantics. Well, ML in general has a formal semantics, CakeML as well. I'm not sure if you had any course, probably not, in formal semantics of programming languages. Formal syntax, yes, of course, you all know what it is, right? BNF, for example, Backus NOR notation for formal syntax. That's elementary. What is formal semantics? Anyone have heard about it? It's non-trivial. So how could you define the semantics of a programming language? So to say formally what this or that language construct does. There are several ways. And for example, you can simply bypass the problem and you can say, my language is translated into another language. And for that language, we assume that we understand what its semantics is, for example. In this case, the formal semantics is called denotational. Or you can really specify your formal semantics through some kind of execution model. So you formally define, for example, the heap and the stack of your runtime system. You define the meaning of all operations. For example, if you define an operation on a local, I wouldn't say variable, a definition in a functional language, then let's say it creates an object on the stack and the stack is updated. If you create, let's say, a list element, then your heap is updated and a new head is attached to a currently existing list. So you have some kind of memory model So denotational is via another language. This semantics is called operational. Via a memory and operations model. It's much easier to say than to express this in detail. But the whole idea is like this. And basically, both actually whole four has both actually denotational and operational semantics. Denotational precisely by translating KML, but it has an operational semantics as well. KML has an operational semantics, which allows us to reason quite rigorously about what our programs are doing. But not only that. KML is a so-called verified compiler. Have you ever encountered, it's unlikely, but it may be, an error in a compiler? So basically, you write a program. You believe that your program is correct. You run your program and you get strange invalid results. You test it and you can't understand why that. And then you read some kind of forum on Stack Overflow in a similar situation. Some people say, yes, you are right, but there is a bug, an error, a fault in the correct term, in the compiler itself. So your program is correct, but the compiler is not. Have you ever seen this? Probably not often, but this does happen. So for example, previously, do you know what GMP is? An open source library called GMP. GNU Multiple Precision, which allows you to create, for example, integer or floating point rational numbers with arbitrary lengths, not limited to a fixed bit size as with machine types. Obviously at the expense of huge increase in computational complexity, but you can maintain arbitrary precision arithmetic. For optimization reasons, because it is compiled with very high degree of code optimization, at some point, not now, not anymore, but with GCC compilers, up to 4.0, okay, nowadays we have GCC 10.x, so that was a long time ago. But with GCC compilers up to 4.0, we usually had huge problems with compiling GMP, and very often it failed and failed self-tests due to compile errors. So compile errors are not at all unheard of. And therefore, this might be okay. So it may be detected by your testing, and you then either switch to another compiler or you modify your source code somehow so the error doesn't manifest itself anymore. But for mission critical systems, including, yes, blockchain systems which are supposed to carry some business critical transactions, this is not acceptable. And that's why you want to use a compiler which is verified, which is guaranteed to generate a valid machine code, at least for a semantically valid source program. And the problem of constructing verified compilers is a very, very, very new one. Up until about 10 years ago, the world computer science didn't know how to solve this problem. only in around 2009, the first verified compiler appeared, created by Xavier Leroy in France for a subset, although a good, usable, reasonable subset of C. So now verified compilers exist for C and for CakeML. We opted to use CakeML because apart from verified compilation, it has many other nice properties. Yes, it is a functional language of ML family with a very powerful type system, as you could see in Haskell, for example, with automated memory management, which is much less prone to let's say pointer or memory errors compared to others. Okay, so CakeML is used for implementation of both actually smart contracts. More precisely, a smart contract is currently implemented in whole 4, translated in CakeML, and finally translated directly into x86-64 machine code. And it is also used in implementation of the distributed ledger system node itself. So all things like network communications, memory management, persistence management, parsing of blocks, execution of smart contracts, and so on, everything is being implemented and part is already implemented in this CakeML language. So we get verifiability, formal verifiability due to the existence of formal semantics of whole 4. We have verifiability of smart contracts. We can use formal verification of CakeML nodes as well. We have formally verified the correctness of the hot stuff Byzantine fault tolerance protocol, which I presented to you, because it is not at all obvious. Obviously, what I gave to you is a top-level outline, but it is not at all obvious that it has a safety property, that it converges to a consistent state, and that it is free of unpleasant episodes, which are called deadlocks, which would mean that components are waiting for messages from each other and none of the components can advance. So it has been formally verified that hot stuff BFT is indeed safe and live. So safety and liveness properties have been verified. And on top of that, if we really need, I would say, very highly mission dependable safety grade execution environment, then we run nodes of this system not on top of Linux, but on top of a strange small microkernel operating system, which is called SCL4 microkernel. That's an outline. So if you would like to know more about this development, or if you are passionate about, for example, functional programming, possibly interested in blockchain, possibly interested in cryptography, in anything like that, primarily the functional programming skills, ML, Haskell, Erlang, F# are welcome, then you are free to apply and join the project. That's all for now. Well done. Thank you.